into chapter 4, section 3 then. Just the camera a little bit so you can see that just a little bit better. Chapter 4, section 3 is about logarithmic functions. So in the last section, we looked at exponential functions. Okay, I'll adjust it, and I think you'll be able to. And so here, we'll discuss logarithmic ones. And if I darken it down, move that up, and move this down. Is that any better? Okay. And it doesn't really help, but we'll try that. Okay, so the first thing we need to do is define a logarithmic function. A logarithmic function is any function that can be written as f of x is equal to the log of x base a is the way that's written. The base is a subscript. And that reads either the log of x base a or the log base a of x. By definition, there's a few things we need to point out here. The a has to be greater than 0. So your base cannot be negative or 0. The a cannot be equal to 1 by definition. And here's the one I really want you to pay attention to. The x must be greater than 0. So you cannot take the log of a negative. Let me repeat that. You cannot take the log of a negative or 0. Now, what does this mean? What does the log of x base a mean? If I replace the f of x with a y, and wrote the log of x base a, that implies the following. It implies that the base a to the power of y is equal to x. So in other words, a logarithm is another way of expressing this relationship over here. A to the y is equal to x. You say, well, why would I want to express it that way? Well, sometimes it's easier to think in terms of logarithms than it is to think in terms of exponents, much like sometimes it's easier to think in terms of division than multiplication. So they're kind of inverse operations of one another, and sometimes it's easier to think this way than it is to think that way. We'll look at some instances as we move along here. So anytime you talk about logarithms, you almost always end up with these kind of problems. And the directions here will simply say rewrite. It might say rewrite as a logarithm, or it might say rewrite with exponents. If they give you something like this, 5 squared is equal to 25, it'll say rewrite as a logarithm. So we would write the log. What's going to be the subscript?
The a.
Yes.
The subscript is a.
5. Of 25. So here's how I remember this. I always remember the base is the subscript, and then the exponent always goes by itself. equals 2. Log of 25 base 5 is equal to 2. So the logarithm always equals the exponent. In fact, one book that I taught out of one time defined a logarithm that way. It said a logarithm is an exponent. So you can see that this is equal to the exponent of 2. Another way to think about a logarithm is, if you just think about these two numbers and their relationship to 2, it's kind of like asking what power do you raise 5 to that'll give you 25. Or you raise 5 to the second power to get 25. So if somebody said, well, that's probably hard to see, but what's the log of 8 base 2? It means what power do you raise 2 to get 8? That'd be the third power. So this is one kind of rewrite problem you'd have. The other kind of rewrite problem you would have would be to reverse it. So maybe they would give you a logarithm like the log of 64 base 4 is equal to 3 and ask you to write that with exponents. So in that case the base is 4, the power is 3, so 4 to the third is equal to 64. So that's pretty simple, not too bad. So the next thing we want to do, now that we know how to rewrite logarithms, is to graph some logarithmic functions. In a few moments, we are going to graph this logarithmic function. F of x is equal to the log of x base 1/2. Now, to get the basic idea behind how to graph a logarithmic function, I'm going to do a little thinking over here on the other side of this line. It can be shown, and I'm not going to take the time to do it right now, but it can be shown that f of x is equal to the log of x base a, and g of x is equal to the a to the x, are inverse functions. If you'd like to see how that's the case, stick around after class sometime and I'll show you that they're inverses. Now, we know that from our last lesson that this second function, the exponential function, goes through the points 1a, 0, 1, and negative 1, 1 over a. And since inverse functions switch the roles of x and y, that means the logarithmic function has to go through a 1, 1, 0, and 1 over a, negative 1. So that's the way I always remember it. I always generate these 3 points with the exponential function, and then I just switch those 3 points to get the 3 key points on a logarithmic function. Not only that, but we said that the exponential function has an asymptote at the x-axis. So the logarithmic function has an asymptote of the y-axis. Now let's see how that would help us on this function here. So my a is a half. So a1 would be a half 1, 1, 0. And so 1 over a would be 1 over a half. If you take 1 over a half, that's 2. and -1. So there are 3 key points on the logarithmic function. Am I making sense, Lexi? Okay, let's graph them and see what our graph looks like. So 1, 0 is right there. 2, -1 is 2 to the right and 1 down, that's there. A half 1 is 1 to the right, or half to the right and 1 up, which is there. Which means the graph, remember the y-axis is an asymptote, so it's going to get closer and closer but never touch. And then down here it kind of flattens out a little bit. Doesn't get completely flat. So that's what the graph of the logarithmic function looks like. Okay, and then the other thing we can do then is we could shift the graph around out in the xy plane like we have with some of our other graphs. So let's try the next example there that's on your notes. We have the log of x minus 1 base 2, and we want the graph. And that's equal to f of x. I just forgot to write the f of x, that's all. So if we use what we've learned in this semester, we could use the log of x base 2 as the parent graph. And then, hey Lexi, what's that -1 going to do to it?
Go right.
It's going to move it 1 to the right. That's right. So let's get this graph and then we'll move it 1 to the right. So A1 would be 2, 1, 1, 0, and 1 over A would be 1/2, -1. Okay, we'll plot those 3. 2, 1, 1, 0, half -1 would be there. The y-axis is an asymptote. So that graph's going to look something like that. And then all of that graph is going to move 1 unit to the right. So 1, 0 is going to go to 2, 0. 2, 1 is going to go to 3, 1. A half -1 is going to go to 1.5, -1. And the asymptote is also going to shift 1 to the right. So the answer to the problem is actually in red here. And I would draw a separate graph to show that then. What do you think? Easy, moderate, or hard?
Moderate. It's not that bad, it's just, I gotta really, think about it, I can't just quickly do it.
Okay. Now, the next thing we're going to do, if you look at your notes, is talk about some properties of logarithms. And really, what we're getting ready to show you here is going to be foundational for working with logarithms the rest of the chapter. And we're going to talk about 3 properties, and we got to get these and get them well. So the first one deals with when I have the log, we'll say base A, of a product, m times n. Now, before I write these properties up, I want you to remember something I said earlier in this lesson. I said that the logarithm is really an exponent. So things that are true for exponents are related to things that are true for logarithms. And we know that when we multiply variables, we add the exponents. So what this property allows me to do is it allows me to bust this single logarithm up into numerous logarithms. And the property says that if you're multiplying over here, then you can add the individual logarithms. Here's what I mean. This is equal to the log of m base a plus the log of n base a. So when you have the log of a product, that equals the sum of the logs. So what if I had the log of a quotient, like the log of m over n base a? Well, think about it. If I add logarithms whenever I multiply over here, then wouldn't that mean I'm going to subtract logarithms whenever I divide? So I'd have the log of m base a minus the log of n base a. Now let's generalize what we've got here. We can make this real simple, real quick. M is in the numerator over here, it's a positive log over here. N is in the numerator on the left side, it's a positive logarithm on the right side. M is in the numerator on the left side, it's a positive logarithm on the right side. N is in the denominator on the left side, it's a negative logarithm on the right side. So there you go. If you come from the numerator, you're going to end up positive. If you come from the denominator, you're going to end up negative. Now we'll use these properties going both ways. In other words, sometimes we'll be given a log that looks like this, and we'll split it up and write it as two separate logs. Other times we'll have a string of logs that are added or subtracted, and we'll go backwards and write them as one log. There's one last property we want to look at really quick. It deals with when I have the log of something raised to a power. Let's say we had the log of p to the r base a. What this property says that we can do is take that power and make it a coefficient out in front of the log. So this would equal r times the log of p base a. So there are three properties. Now, it's kind of all theoretical right now, so let's try to make some sense out of how we're going to use them a little bit. Well, I just failed to record the last 6 or 7 minutes of this lecture. So your assignment for Chapter 4, Section 3 is on page 423. It's on your notes. So if there are some problems you run into that you have trouble with, make sure you ask about them or come see me. If you're having trouble, come see me on my office hours. Okay.